In this example, what we're going to look at is, well, what if rather than we want the area, or sorry, the volume under a surface and above the xy plane, what if I want the volume bounded between two surfaces? So we're going to kind of analogously think back to, well, what did we do when we wanted area between two curves, right? When we wanted area between curves, well, we did a subtraction. We said if you think about those areas, right, you've got kind of the total area under the top curve and then minus the total area under the bottom curve gives you the difference. So we can do the exact same thing here where we can think about the values of wanting those subtractions. So really we're going to do the volume, we're going to integrate over some region, and we can kind of think about, well, we need to do top minus bottom. So it's kind of like we need top surface minus bottom surface. And we're going to integrate over the region of that area. So part of this I can set up already, where I can see, well, my top surface, notice I drew them over here, right? We're above the plane and below the paraboloid. So when we picture it, right, that paraboloid is kind of that parabolic dome, if you will, coming down, and then we're cutting that with a plane. So we're kind of left with this little domed piece right here. So it's got kind of a roundish bottom and then like a domed top to it. That's the volume chunk that we're looking for here. So my top curve then, right, the one that has larger z values, that's why we're doing top curve, bottom curve, so bigger minus smaller. The top one would be the paraboloid, which would be the 1 minus x squared minus y squared. And then the bottom curve would be the plane, which we just want the z part of it, which would then be minus that 1 minus y. And then we're doing this with respect to area. So what we still have to find for this problem is, well, what is R, right? What is the region that we're doing this over? Now you need to kind of picture R as being like if I shined a spotlight right on top of this little piece that we're finding the volume of. Well, what would that region in the xy plane look like? What would the shadow look like if I shined that light on top? Well, if we think about it, it's going to be dependent on this boundary curve, right? What is this curve of intersection between those two planes? Because that's really going to be the boundary of my region R when I shine that spotlight down onto it. So that wasn't given to me. It's something that we need to find. So we need to find the intersection curve. So if we look for that intersection curve, well, it's where z equals z. So it's where 1 minus y equals 1 minus x squared minus y squared. Now notice what we're going to get when we do this is we're going to get a curve, right? We're not going to get specific numeric values. We're going to get some sort of curve in terms of x and y. Now if we look at this one, probably what we can see is we've got x squareds and we've got y squareds. It's probably going to be something related to a circle. So let's move those x squared and y squareds over and move the constants over to the other side. So we've got x squared plus y squared. Let's do the minus y. And really, once I subtract the 1 over, it's going to be equals 0 on the other side. Now, when we think about wanting to represent this circle, how we're used to seeing it, to be able to see where it is, we want to see the center and we want to see the radius, which means that we need to write it as, right, x minus something squared plus y plus or minus something squared equals that r squared. And what we're going to do is complete the square, which is delightful. So you can look up and remind yourself of how to do these, but if you remember to do that completing the square, we look at what our B value is to think about what we need to add and subtract to both sides. So we look at that B value we have here is a -1. So we're going to add, remember it's B over 2 squared to both sides. And really what we're actually using is a little negative B over 2 squared, but the negative gets changed out once we square it. So in this case, then this would be really 1/2 squared, and that would be to both sides, because what we'll see then is I've got x squared plus y squared minus y plus a 4th equals a 4th. When I look at this term now, when I try and factor y squared minus y plus a 4th, well, if I do y minus a 1/2, then what we end up with is, right, you get y squared minus a 1/2y minus a 1/2y, which is your minus y, and then -1/2 times -1/2 is plus a 4th, and then this is all equal to a 4th. So it's a circle. We've got a center. It is at x equals 0 and y is a 1/2, and then my radius, remember this was squared, so in this case my radius would really be r equals a 1/2. So when we're taking a look at drawing this then, we've got a 1/2 right here, our radius is another 1/2. So we're going to have our circle right here. So our region R in this case is a circular region, a little more difficult than the triangular regions we've been doing, but definitely something that we can handle. So we need to think about how to do it a little bit, right? We can either think about a top curve, bottom curve, or a right curve, left curve. In this case, it doesn't make a huge difference except for the fact that, well, it's probably easier to solve for x in this just because y's got some extra stuff attached to it. So notice if we take this and solve it for x, we would end up with x squared is equal to a 4th. Well, let's actually solve this one for x, because we don't need to do the squared version because we would just simplify it anyway. So if we solve this one for x squared, well then we have y minus y squared, so then we would do a square root, but remember we get a plus minus. So x is going to be plus or minus the square root of y minus y squared, which we have to think about what do those plus and minus mean. Well, remember it's the 2 halves of the semicircle, right? The negative one is the bottom semicircle and the positive one is the top semicircle. So in this case though, it's in terms of x's, so it would really be the left semicircle and the right semicircle. But it's the 2 halves of the circle. So what we would end up with here is we would have x goes from the negative square root, so negative square root of y minus y squared, to the positive square root. So that's that left semicircle to the right semicircle. And then if we think about y's, looking at what's the smallest y value, what's the biggest y value, well the smallest is 0 and the biggest is 1. So these would be my bounds to define R. So when we come back over here, we would have that this equals the integral. We had 1 minus 1 cancels out. We've got a negative x squared. We've got minus y squared. And then really plus y. We ended up doing x as our function bound, so it's going to be dx dy. And x goes from negative square root y minus y squared to positive square root y minus y squared. X, and then y, goes from 0 to 1.